Okay, thank you for the introduction, Jack. So this is really work that was done by my colleague Markus Müller from University of Innsbruck, who can't be here, so I will be just presenting his work, and we have a lot of co-authors, which you can see here. So Chelsea has briefly introduced this nice new analytical tool, which is the PTR-TOF, and since early 2013, in the frame of the Discover AQ campaign, we are flying an airborne PTR-TOF-MS. So here you see a picture of the instrument. It's not exactly the same instrument Chelsea showed, because that's the high-end and very expensive version. So this is a somehow cheaper version, half price and much smaller. So the flight tube is only 20 centimeters long, and that's why we call it compact PTR-TOF in the literature, although the instrument itself is not compact. And you can find the details on this instrument on this recent publication in AMT. And so the concept is basically, the source is the same. You have an H3O plus source, and here you bring in your air sample, which you protonate and the organic compounds, and you analyze them in the time of flight mass spectrometer. Here's the performance characteristics of this new instrument. So the sensitivity levels, what we have is about 60 to 150 counts per ppb, which is pretty good, not as good as the current high-end versions, which are a factor of maybe 7, 8 higher. Limits of detection are between 50 and 450 ppt at 1 second. 450 is the problem is we have, when we run it on the plane, we get power maybe 2 hours before, so some of the organics, we have high background. But typically for the higher, for most of the compounds, we're around 50 ppt, so that's pretty good. Here you see the major difference as compared to the instrument Chelsea showed before. We have a mass resolution of only 1500 and not 5000, so that somehow limits our identification capability. Still, we are good enough for M over C less than 120, let's say, to identify the SAM formula. And here you see the same example Chelsea showed about mass 69, which is a sum of furan and isoprene. We're not that well resolved, but we're still able to resolve it. So with this performance characteristics, we can measure at 1 Hertz in the polluted boundary layer, and if we go to point sources, we can measure 10 Hertz. And the data I'm going to show today is part of the Discover AQ campaign, although it's not really Discover AQ. It was obtained during the transit home. So we did, even during the transit, we did some good science. Bob Yokelson and myself convinced Jim Crawford to spend half an hour in Georgia here, sampling this tree logs and understory fire, and Bob had somebody drive there to check out what it really was, what type of fire, and so it is, basically trees had been cut out and all the remainings and the understory was burned afterwards. So here you see the sampling maneuver you did. So yeah, we came in here, and what you have color-coded here is a radar altitude. So we came in at altitude, dropped down over the fire, sampled the emissions, the direct emission over the fire, and then followed the Plume 13 kilometers downwind, and then at an average wind speed of 3.5 meters per second. This corresponds to an aging time of about 60 minutes. Then we turned around, did the transect, so we get the transect of the Plume, went back to the source, again sampled the fire, turned around, sampled it the third time, did the transect, looked at the aging for 1 hour, did another transect 1 hour downwind, and sampled the source for the fourth time. So 2 transects, 1 hour downwind, and 4 overpasses or direct emission samplings. So here you see a picture from the front camera, and we actually see it's a rather small fire, and it consists of two smaller fires. So we have two small plumes, and here this picture shows you the analytical power of this new instrument. So this is, note that from here to here this is 5 seconds. So we get, if you measure 10 Hertz, we even get, when we measure point sources, we get very good signal to noise. So we are able to resolve even these small plumes, and Markus has calculated this. So at 10 Hertz we have a 10 meter horizontal resolution and 1 meter vertical resolution. So we can really sample these plumes properly. And so here is the emission ratios we determined. We don't have that many points because now PTR-MS is no longer the slowest sensor. Now it's CO, the limiting factor. So I hope we initiate a competition here. And so this is the emission ratios we get for acetonitrile, furan, monoterpenes, isoprene. Unfortunately, this is Marcus uses ppb per ppb. You should probably use ppt per ppb. So it's 1.5 ppt per ppb in acetonitrile, which you typically find in the literature. But this is the first time we have these. We have characterized this at high time resolution for furan, and you see in mass 69, it's about 50-50 the contribution from these two compounds. Monoterpenes, benzene, toluene, C8. C8. So we get, here it's again the sum of the C8 alkene benzenes and C9 alkyl benzenes because we still cannot resolve isomers, of course. This is also another major advantage of this TOF. It's not only that you can sample so fast, but also that you sample the whole mass spectrum at this rate. When you run a conventional PTR-MS instrument, it's a quadrupole, so you sequentially measure your compounds. So before the flight, you have to choose what you want to measure. So I say I want to sit at this and this and this and this mass. I typically use 10 masses. You sit 1 second on each mass, and then you basically pre-select what you want to look at. Here you get the full information. You don't need to pre-select, and so that gives you a chance to discover new things. You're not only looking for what you already know it's there. And so here, this is a mass scan obtained in this fire, and what you see in dark gray here is the signals we typically monitor with a quadrupole instrument. So we choose like 10 to 15 masses to have a time resolution of 10 to 15. This is what we typically measure, and all the peaks in light gray that we have is things that we have overlooked in the past or we haven't been looking in the past. So, and then, of course, the interesting or the important thing is to find out, to identify and to quantify, or tentatively identify and quantify what else is in that plume. And so Marcus has made a list of the compounds with the highest emission ratios that we have found. So this is a list of 10 to 15 compounds. So, and here is the emission ratios, everything. This basically lists all signals higher than 1 per mil of CO. And so the highest one we found is formaldehyde, methanol, which is known, acetaldehyde. This is an interesting compound. It's 2-furfural with like almost 8 ppt per ppb emissions. 43, it's a common fragment of many VOCs, so we can't really assign it to a specific compound. Acetone propanol, that's known. Mass 30 is nitrous acid, so even though it's not the VOC, PTR-MS measures a few inorganic compounds like ammonia and nitrous acid. I'm not sure this is the right number. He has used the right calibration factor for nitrous acid. I think this will come up quite a bit. Acetic acid, glycolaldehyde, these are isomers, so unfortunately we cannot resolve them. MBK, metacholine, benzene, methyl glyoxal, isoprene, and some further oxygenated compounds. But even though if you're not able to maybe not able to identify all the compounds, we can still tell or identify the sum formula. And so this is the distribution in terms of carbon atoms what we find in here. So this is the relative contribution of VOCs with 0 carbon atoms, 1, 2, 3, 4. I mean 0 is yeah. And so you mostly see, I mean C1 is formaldehyde and methanol, and then you go higher up, so we see it all the way up to C12. There's maybe only a minor contribution, and we can do the same thing with oxygen. So again, mostly singly oxygenated species what we find, and here is just some parameters we have put together to give you an idea about a summary on the fire. So the MCE is 0.9. We have a 9 ppm enhancement in CO2, 0.9 ppm enhancement in CO, and 1.3 in acetonitrile. This is interesting then because it's often reported the O2C ratios in the gas phase. So we start off with 0.2. Okay, then again the same maneuver, and now what we do is we look at the emission and we look what happens 1 hour downwind. And so this is again the enhancement ratio or excess ratio over CO at the source, and this is the excess ratio at 1 hour downwind. And this is the signals that actually get lost, and these are the signals that get produced. And so I think I don't have the time to go through all this. I just want to go to the compounds highlighted in bold. So these are the ones that really see a clear loss over this 1 hour of aging. So it's 2-furfural, and I will go back to this one a little bit later. So more than a factor of 3 loss on the way downwind. Nitrous acid, of course, is rapidly photolyzed. We have isoprene and furan. And the compounds that are being formed is formaldehyde, acetic acid, glycolaldehyde, maleic acid, and formic acid. And so we can do the same exercise we did before when we look at the carbon atoms and the oxygen atoms. So this is in light gray is the source, and in dark is 60-minute age. So you see that the singly with 1 carbon increase, with 2 increase. So fragmentation is a common process, but some of the compounds also like increase downwind. And not surprisingly, a number of oxygen atoms increases, so it's obviously they get oxidized. And so the O2C ratio increases from 0.2 to 0.6 within 1 hour. And then, this is the part I like the most, so we flew 1 hour downwind, and we followed, the pilots nicely managed to track the plume, or stay within the plume and sample it. And here is the concentration corrected for dilution using the CO signal. And so what you see is here, this is in light blue, you see the drop, for example, in 2-furfural, which we know has a OH reaction constant of 3.5 10 to the minus 11. And from that we can derive an OH radical density, or an average OH radical density of 8.5 10 to the 6, which is in good agreement with what people have seen before. And so you see the same thing with the 3 compounds of 4 which I indicated in the list before. So the decay in furan, and decay in isoprene, and the increase in acetic acid. So, and this is the last slide where we looked at the ozone formation. Again, this is not the absolute value that was formed in terms of ozone, so it's not 50 ppb because we had a factor of 13 dilution, so we have formed maybe 4 ppb. But you see that there's big potential for ozone formation if, around 50 ppb corrected. This is the NO and the NO2. He should have put on the NOY, but we didn't manage. And one interesting thing is also the particle formation. So if you have, this is again dilution corrected. If you have 47 microcubic meter per centimeter, assuming density of 1.3, it's 60 micrograms per cubic meter. And if you look at our budget in the loss in the gas phase, we lose around 30 micrograms per cubic meter. So that's roughly half of the mass we see in the gas phase, but of course you get oxidized and you have inorganic compounds, so that's in good agreement. And that's all I have, and it's 1 second, so you can read the summary yourself. Thank you.
We do have time for a question or two.
How do you assign formulas to your molecular masses?
It's a chemically educated guess. Basically, you look in the literature, what has been measured, what has been identified, and so then you come down. I mean, with the small signals, it's easy. Like for methanol, there is no isomer, there is no other possibility. So methanol, acetonitrile, acetaldehyde, there is no other options. So of course, the higher you go, the more difficult it becomes. And then you look at what is available in the literature. Then you look at the time evolution. Then you see if it is a reactive or non-reactive compound. Then you can narrow it down. There have been a number of comparisons in the past with WAS and with TOGA, which are GCs. So we know, we have a good idea, and then we give an assignment or a tentative assignment.
Then the question is, what is the error of your formula assignment? Do you have some error to something like that?
You mean the mass accuracy? Yeah, we have mass accuracy of around 10 ppm.
One more question, I guess, Dan?
Some of your, at least one of your loss rates seem rather high, like the acetonitrile. Want to comment?
Okay, that's the. I mean, I didn't like that either because the acetonitrile is a long-lived compound, like several months. But can I go back just quickly? Okay, so where do we have the acetonite? Here we go. Okay, so here's the acetonitrile. So it's from 1.5 plus minus 0.2 to 0.9 plus minus 0.2. So it's okay, it's statistically relevant, but barely. And the other thing is, of course, the fire has some natural variability. And so if we didn't really sample it at the same time. So that's the only explanation I have that we see. You know, it may have emitted a little bit less acetonitrile when it was emitted actually at 1 hour before, and that's why it dropped. But that shows you clearly also the limitation of this method. That's why I wanted to put the focus on those where we really see a clear decay.